So this is some feedback for quantitative task 1, determination of an enthalpy change using Hess's law from May 2009. It's a reasonably straightforward task, just using Q equals MCT and a little bit of Hess at the end. So you can see the instructions for the procedure that you undertook during the lesson. There was one error in the instructions, which was just here, where they've put K2CO3 and they actually meant the KHCO3. So the marking points come from, first of all, one mark for the table here and another mark for the table here. You have to ensure that on both cases you have recorded to a consistent number of decimal places. For the first one with mass, it's 2 decimal places or 3 decimal places depending on the balance that you've used. And for temperature readings, it's initial and final temperature with a 0 or 5 as the final digits. You also need to make sure that your subtractions are correct for both of the readings. And finally, the place that most students lose marks is that here, where we come to do the subtraction, and here again where we come to do the subtraction, the decimal places differ, and for the temperature in particular, that people forget to put 0.0, so that would lose marks for the table. The accuracy marks are just based on your practical and how close your practical results are to my practical results. So if it was, on this case, if it was within 2 degrees of mine, you get 1 mark, and 1 degree of mine, you get 2 marks. So that's just a measure of how accurate and precise you've been during your experimentation. The calculations, we've got Q equals MCT. Q, the value that we're trying to find out. M is the mass, which in this case is 25, and you know that it's 25 from step 2 of the instructions, 25 centimetres cubed. You've then got your 4.2, which is your specific heat capacity, and your specific heat capacity is given to you in the question. You do need, for A2, to know specific heat capacity of water or of an aqueous solution is 4.2 or 4.18. That is now a standard that you have to remember. Delta T is what you get from your table. My table is 8 degrees, but yours might be different. So your values that you get for this experiment will be different. Q equals MCT for mine gives me a value of 840, and the units are included as joules. Calculating the amount in moles that we've used in our experiment using N equals M over M. 3.44, this is our mass, which we've got from our table. 100.1, this is our molecular mass, which we get from the periodic table. And then we've got our answer here, which for my particular mass used is this, but it will be slightly different for yours. Calculator value is accepted, or it can be rounded to 3 significant figures. Both are acceptable, as the question doesn't mention anything about decimal places or significant figures. The next one, the enthalpy change in kilojoules for the reaction of 1 mole of KHCO3. All experiments like this, you take the value that you're calculating, so energy, which is our answer from A, we divide through by the number of moles we've calculated, which was our answer from B, and I end up with 443. I have to remember that this is in joules, and therefore convert to kilojoules by dividing 3 by 1,000 to give me 24.443. Again, there is no indication on significant figures, so calculator value is acceptable, and more or less any value is acceptable, to be honest, as long as it's 3 significant figures or greater. The sign is important. If there is an absence of a sign, it will be assumed that you mean it's positive. In this case, it's good to get into the habit of writing positive or negative. And this one is endothermic, and we know it's endothermic as the temperature change was decreased when we looked at the table record. So my temperature went down, and therefore I know what my sign is going to be here. Right, so on to the next question. Again, another series of instructions. 2 more tables for 2 more marks, consistent decimal places, including in the calculated subtraction, and for temperature, a 5 or a 0 must be the end value, and again, making sure to put that 0.0 if you've got calculations as such. Same calculations as earlier, so we've got Q equals MCT, again, 25 centimetres cubed from 0.2 in my instructions from my experiment, C 4.2 is given to me in the question, and 2 degrees from my table. So when I looked at my temperature change, my temperature change was 2 degrees. This gives me a value of 210 joules. Units are already included. Make sure that you keep it as joules. 2, calculate the amount in moles of the substance that you used. Same as last time, N equals M over M. Mass from the table, molar mass from the periodic table, which gives me a value of 0.015123. Next question, coming down, same as last time again. So the energy that we have divided by the number of moles we have to get it in energy released per mole. So that's the answer to D part 1 divided by the answer to D part 2, which is energy divided by moles, and you can see the numbers that I've included here, which gives me 13,886 joules, again converting into kilojoules, which gives me 13.886. In this case, because my temperature went up, it's an exothermic reaction and therefore my delta H is negative, so I have to make sure to include that sign. Significant figures are not stated, so I've not worried. Extra things to note, here you can see that I've just written part of the calculator value. When you're doing further calculations, use the whole calculator value. So I've only written up to the 3, but the number that I input into the calculator was actually the full value. And that just means that you don't lose marks for rounding incorrectly. So use the full calculator value whenever you're doing calculations, particularly for moles that follow through. The last question is a Hess question. Here we've got delta H1. We know that that's delta H1 if we look at our experiment from earlier, and here from here to here the black arrow is our delta H2. I've put both of the symbols and both of the numbers there so that I know what I'm talking about when I come on to do my calculations. If you did delta H1 take away delta H2, delta H1 take away delta H2, you get 1 mark. If you did 2 lots of delta H1 take away delta H2, then you picked up both marks. Here to here, even though it's a 2 to 2 ratio, we have to remember that the enthalpy change that we calculated earlier was per 1 mole. So this number here represents 1 mole of KHCO3 being converted into 1 mole of KCl. So I have to double up this value when I'm doing my calculations if I want to get my enthalpy change correct. Now there's a couple of different ways of looking at Hess's cycles. The way that I like to do it myself is always have it going from here and then down and then looking at it going back up. So you can see here on this side of the black arrow I've done a red dotted line. That red dotted line represents to me the enthalpy change if I go from here to here. The value is exactly the same as the calculated value, 13.886. However, I've flipped the sign. So going from here to here is negative, therefore going from here to here is positive. So the way that I always calculate my Hesses are like so. I've got my 24 value, I've multiplied it by 2 because I've got 2 moles, and then I'm adding, and I always add my second value, which in this case is going to be 13.886. I've flipped the sign as I've flipped the arrow. So just again, and again this is my way of doing it, there are different ways. I don't say delta H1 minus delta H2. In my head it makes more sense to always follow through the pathway from there down and then all the way back up. But for me it means that whatever sign I've got going in this direction, I have to flip the sign if I'm looking at the pathway going in that direction. If that makes sense, brilliant. If not, and you prefer to use an alternative method, which is delta H1 minus delta H2, then again, as long as it works for you and you get the right answer, then that's absolutely fine.